Alright kids, we're gonna finish up Newton's laws. We're doing some more, spicy problems with multiple parts. They're not that hard. You can do it. I believe in you. You just have to break the problem and break the system into multiple objects. And remember, Newton's laws are true for each part and the whole system. Actually, before we get into that, we're gonna look back at traffic light problems. So I'm gonna do a lot of derivations today. Hopefully I can finish before like hours and hours pass. But let's see a traffic light problem. A traffic light problem is a mass hanging from two cables or strings. F1, theta 1, F2, theta 2. Not always exactly like this, but it's a 2D free body diagram problem where the net y force and the net x force must be 0 for this object, traffic light or whatever, to be in equilibrium. So we have two equations. Like so. If you're stuck, draw a free body diagram. But the diagram is basically a free body diagram in this problem. These are the x components of the forces. These are the y components. F1y, F1x. This one's F2x, F2y. Okay, and hopefully you know how to find F1x, F1y using sine and cosine. That makes these two equations F1 sine theta 1 plus F2 sine theta 2 minus mg. I made it minus mg because the weight is downward, negative. In this problem, F1 is to the left, F2 is to the right, so I'll make this one negative, this one positive. Theta's not the same. That would make this problem a lot easier, but it's not. So, rearrange this to get two nice equations. So that's basically how you solve the problem. Usually in these problems, you're given m and the thetas, and you're finding both f's. You have two unknowns, so you need two equations, and you have to solve the system of equations. In this case, it's much easier to solve. I'll solve for f2 and plug it in here. And plug it in here, I get, is this going to be cut off? If I write it really f1 sine theta 1 plus f1 cosine theta 1 over cosine theta 2 sine theta 2 equals mg. It is long, it is messy, but there's only one unknown, f1. So solve this for f1, then plug it in here to find f2. You can simplify this to sine theta 2 over cosine theta 2, just tan theta 2. It doesn't really help you very much, but that's how you'd solve a traffic light problem. How is that? Tell me how amazingly simple it seems now that you've seen it done. Yeah, no, it was great. Okay, two more really common problems besides half Atwood. Right, they're kind of the same thing. Like a tower, like the tower of people we saw about that like tower going to Spain video, or like a wedding. That's a stack of blocks, or maybe Maybe like a bunch of people, a bunch of climbers trying to climb up a cliff. We're not going to solve these, but they're the same thing. If I have three masses, M1, M2, M3, or three people, M1, M2, M3, and they're in equilibrium, it's very easy to solve. First, for complex problems with three objects, draw three free body diagrams. 1, 2, 3. They're two together. Let's stick with the climb block. I was in blocks later, so I'll do that by mistake. Free body diagram for person 1. I don't know what they're pulling with. Maybe they're holding on a rope. So I'll call it FT. It doesn't really matter what you call this top force. I call it tension. Well, FG is going to be M1G. Oh, but there's one more force. The force from person 2 on person 1. Uh-oh, we don't know this force or this force, so we can't solve. Well, let's move on. Person 2. Person 2 will have FG and 2G. Hopefully that's pretty straightforward. Person 2 is not affected by the rope, so we won't draw FT, but we'll draw a force pulling up from person 1. So here's a force from person 1 on person 2. And there's one more person. Whenever you draw free body diagrams, think, what's pushing or pulling on this object? Person 2 is being pulled down by person 3. I don't really know which is bigger between these two, but it doesn't really matter. F3 1. No, F3 2. The force from person 3 on person 2. Now let's draw the third free body diagram. Again, this is FG. Person 3 also has an FG. M3G. Does person 3 have a tension downward? No, no one's below person 3, pulling them down, so no issues there. Person 2 pulls up on person 3. And that's it. That's the full free body diagram for person 3. So we have three free body diagrams for 3 people. You can solve for F23 because you know M3 and G. What do you do next? We want to find FT. We can only find F2, 3, the force from person 2 on person 3. What do we do next? Any ideas? Tell me one now. What's that, babies? Oh yeah, great job. Thanks, babies. The force from person 2 on person 3 must be equal and opposite to the force on person 3 from person. I said it wrong, but you get what I'm saying. The force from 2 on 3 is opposite the force on 3 from. I said it wrong again. This is the force from 2 on 3. This is the force from 3 on 2. They're equal and opposite. So if we know M3 and G, we know this. Well, that, we know this. This is just calculation, so we know that. If you know these two, add them together, we got this. This is the same as this. Again, third law. So now we know this, we got FT. There's also, you can do a shortcut, as you saw. Look at these 3 diagrams. We have 3 free body diagrams. How can we use these 3 free body diagrams to make a free body diagram for the system? So based on these, what do you do to get the free body diagram for the system? Tell me right now. For the system, F21, F12, F32, and F23 all cancel. They're all internal forces, so we won't draw any of those forces. On the system, the only forces left are Ft, Fg1, Fg2, Fg3. So it's a much simpler problem. And of course, if you wanted to make it even easier, you can combine all three of these forces of gravity into one. M times G, or M is the sum of M1, M2, and M3. So it was pretty obvious if you thought about it, but this is how you explicitly find Ft. Ft will be M1 plus M2 plus M3 times G. But if you wanted to make it more complex, you would have to break it down and find F2 on 3, the force from person 2 on person 3, or the force on person 2 from person 1. Those you need to break it down, because in the system free body diagram, they kind of disappear because of the fact that they're internal forces. So great job. I think I can do one more problem, and I'll try to put in some numbers to make it more physics-y. So yeah, here's the problem. I had 3 blocks. One kilogram, 3 kilograms, 2 kilograms. Thank you. And they're all being pushed by a big force. Hopefully these numbers work out. 60 newtons. Okay. We want to find the force. Let's keep it simple. The force between these 2 blocks. Both of them. We'll find both of them. So the question is, determine the normal force between these 2 blocks, normal force between these 2 blocks. I'll call them A and B. Okay. First step, treat the whole system as one object. I'm going to do it in my head because I'm so smart. A will be 10 meters per second squared. Okay. Now, look at just block 1. Obviously block 1 is this one. So just for block 1, draw the free body diagram. Fn, the upward force from the ground. Fg, the downward force from gravity. We could find them. We don't need to, they don't matter. They add up to 0. Fn, yeah, force F is applied to block 1. So that's 1. And there's one more force. The normal force right here is acting on block 1. Are they are they equal to each other? Do they add to 0? Do they cancel out? There's many ways to say it. Are these 2 equal? Tell me right now. They are not equal. Block 1 is not in equilibrium. If block 1 were in equilibrium, F net on block 1 would be 0. But it's not. F net, let's say right is positive. F net is 60 newtons minus this force because it's left. That's fine. Well, what's F net over M? It's A, 10 meters per second squared. It's very messy. I made my drawing too big. I apologize. Well, what's M for block 1? Again, we're talking about block 1, not system. So it's not 6 kilograms, it's 1 kilogram. Solve this. Solve this. Come on, brain, solve it. 50 newtons. Multiply both sides by 1 kilogram. 10 kilogram meters per second squared is 10 newtons. A kilogram meter per second squared is the derivation of a newton. A newton's a derived newton. So 60 newtons minus Fna equals 10 newtons. 6 newtons minus 10 newtons equals Fna. Fna is 50 newtons. We did it. We did half of it. We found the normal force between these two blocks is 50 newtons. We can do the same thing for block 3, but we don't have to. It actually ends up being easier if you, I should erase that. If you look at block 2, the last block. For block 2, the free body diagram is even simpler. See, here's the picture. Normal force upward from the table. Fg downward from gravity. They don't matter. Unless the block's going to start flying or start sinking to the ground, they must add up to 0. Fnb is the only force, so it's net force. Net force over mass is acceleration, which is 10 meters per second squared. And m, well, we're talking about block 2 only, so it's 2 kilograms. Fnb is 20 newtons. We are scholars. We solved it, and it was much easier because we only looked at block 2. But just to check our answer, let's try block 3. So block 3, we, as always, have the normal force and force of gravity. In this case, they don't matter. That's not a rule, but in this problem, if the blocks stay on a level ground or level table, they do not matter. Well, there's only 2 forces on block 3. This one and this one. The block 1 force from the right is the positive one. And the block 2 force from the right to the left is the negative one. Fna, we said, is 50 newtons. Fnb, we said, is 20 newtons. How do we find the acceleration of block 3? And what should it be? Tell me right now. Oh yeah, that was really good. I heard you so loud and clear. The net force over the mass is acceleration. And it should be 10. Well, 50 minus 20 is 30 newtons. F net over m is 30 newtons over the mass, 3 kilograms. Oh my gosh. We got the right answer. We are physics geniuses. We're all going to get 5s on the AP.